Chapter 15 review. So we are looking at a particular formula and we have to answer all these questions. Why is this substance an acid? So this is why this substance is an acid. I'm looking at the carboxylic functional group. This is the functional group that will ID the compound here. We call this an acid because of the carboxylic group. How many carbon atoms are in oleic acid? So I'm going to start counting. I see there are 7 carbon chain at this location, 7 carbon chain at this location. So there are 14, 15, 16, 17, 18. So when I am counting 18 carbons, when I'm counting the carbons, I'm also counting the carbon with the carboxylic acid functional group. Is this fatty acid saturated, mono unsaturated, poly unsaturated? I see one double bond. So I will call this mono unsaturated. Unsaturated is wherever there is a double or a triple bond. I see a double bond. It's not polyunsaturated, mono. Is it most likely to be solid or liquid at room temperature? Again, going into the properties of acids, these mono unsaturated acids are liquids at room temperature. Any unsaturated acid is liquid. If it is a saturated fat, that would be a solid at room temperature. Would it be soluble in water? It would not be soluble in water, even though it has a polar head. There's a carboxylic group that you see is hydrophilic, but the entire chain of carbons there are hydrophobic. Now we should be familiar with the terms. So it should be insoluble. The long hydrocarbon chain makes it insoluble. So this is your solution. All the different questions are answered. So that is one example. So looking at all these formulas, we are able to figure out the number of carbons, all that stuff. So fatty acids. Palmitoleic acid is a fatty acid with the following condensed structural formula. How many carbon atoms? So again, we are looking at 5 carbon chain, 7 carbon chain, that makes it 12, 13, 14, 15, 16. So I'm counting the carbon on the carboxylic group as well. Is this fatty acid unsaturated, saturated, mono or poly? Mono unsaturated. Is it most likely to be solid or liquid at room temperature? Because of the unsaturation, it is going to be a liquid at room temperature. Did we go? Draw the condensed structural formula for glyceryl tripalmetolate, which is used in cosmetic creams and lotions. So we are into esters now. What are esters? Esters are compounds which are formed by the reaction or esterification glycerol and 3 fatty acid molecules come together to create an ester. So the acid involved, 3 molecules of palmitoleic acid and a molecule of glycerol, that's where the glycerol is coming from, combine in the process of esterification to give you this molecule. So looking at the name, you will be able to determine what are the components that came together. So you should be comfortable setting up a molecule of glycerol. Glycerol is a triol, 3 OH molecules in one, 3 OH groups in one molecule. And palmitoleic acid, you have to go back to table 515 on page 515 to look up how do you set up palmitoleic acid. How many carbons? Is there a double bond or an unsaturation or not? So analyze glycerol and 3 palmitoleic acid molecules. So here you have gathered information. you have glycerol, 3 palmitoleic acid, 16 carbon, 1 double bond, and the bond is ester bond. So esterification happens with these 2 molecules. Now, draw the structure. There is your glycerol molecule, 3 hydroxyl groups are here, and this is your palmitoleic acid, 3 molecules, and this is your ester bond. This is where the esterification happens. So you eliminate a molecule of water at each ester bond, and there is your structure of the triglycerol. This should be comfortable. You should be able to comfortably draw this structure based on the information you have. Draw the condensed structural formula for the triglycerol containing 3 molecules of myristic acid. Again, this will be given to you. If not, look up on page 515. 14 carbons, no double bond. So this is a saturated fat, no unsaturation, 0 double bonds. So you are going to again set up the glycerol molecule similar to this setup, 3 OH, and set up myristic acid molecules in 3 locations. Connect the carboxylic and the hydroxyl, eliminating a water molecule at each location, and you have your ester. So please practice setting up these molecules. Now we are looking at reactions of lipids. Write the equation for the reaction catalyzed by the enzyme lipase that hydrolyzes glyceryl trilaurate during the digestion process. Again, lipase is an enzyme that is present during digestion. This enzyme breaks down the fat molecules that are in the diet, in the food during the process of digestion, breaks it down into smaller, more absorbable components. So hydrolyzing at any point is breaking down. So where can you break down? Where there is a bond, you can break it down. Now you're looking at a compound, glyceryl trilaurate. So you are looking at this, and this is an ester, and there is an ester bond in that molecule where you can break the molecule into 2 parts. So glyceryl, glycerol, lauric acid is 3 molecules of lauric acid, laurate. So now we are going to analyze lauric acid information. What are the reactants? This is your reaction, and this is lauric acid, 12 carbons with 0 double bonds. 12 carbons with 0 double bonds. You see, you set up this 10 carbons. 1 starts the chain. There is 1 CH3 to start the chain, 10 carbon chain, and this is the 13th carbon, sorry, the 12th carbon with the carboxylic group. So this is what you are setting up. So there is your enzyme lipase, that is the catalyst for this process. Hydrolysis is breaking down. So this is your bond, ester bond, where the break happens. You are getting your glycerol molecule. This is a glycerol. Remember, we said 3 hydroxyl groups in 1 molecule. And this is the acid. And this is where you eliminate a water molecule, HOH, and you get the ester. You go through hydrolysis, you get the glycerol back. So this is hydrolysis. The reverse is esterification. Okay. So reaction of lipids, hydrolysis, breaking down. What is the name of the product formed when a triglycerol containing oleic acid and linoleic acid is completely hydrogenated? Okay. We have oleic acid and linoleic acid. Let us look up what are these acids, how many carbons? Is there a double bond? Where do you find the information? You are going to look up on page 515. So I am going to look up page 515. I would suggest you look up 515 as well. Oleic acid has 18 carbons with 1 double bond. Linoleic acid has 18 carbons with 2 double bonds. So oleic acid has 18 carbons, 1 double bond. Linoleic acid has 18 carbons, 2 double bonds. Now, when I am hydrogenating these oils, what am I doing? I'm adding hydrogen. So where will the hydrogen go? Go towards the double bonds. So it will go to the 1 double bond in oleic acid and the 2 double bonds in linoleic acid. So now these are saturated, no unsaturation. So this will result in 18 carbon fat with no double bond. So let me go. 18 carbon, no double bond is stearic acid. So when we are hydrogenation happens for oleic and linoleic, you get stearic acid. Okay. Okay. So we did this. Glycerophospholipid structure. Draw the condensed structural formula for cephalin is the glycerophospholipid. It contains 2 stearic acid, first and second carbon with serine and amino alcohol is our amino alcohol, and of course there is a phosphoric acid group also. So glycerophospholipid has a glycerol molecule, 2 acids, and here we see stearic acid, an amino alcohol serine, and a phosphoric acid. So we are going to connect all these molecules. So 2 ester bonds, 1 bond with phosphoric acid and 1 amino ester. So there it is. So this is our glycerol molecule. We started off with the glycerol molecule and we took 3 stearic acid is 18 carbon, no double bond, 16, 17, 18. So 2 molecules connected through an ester bond to these 2 hydroxyl groups. This is your phosphoric acid. You are connecting the phosphoric acid to the 3rd hydroxyl, eliminating a water, connecting. This is your amino alcohol. And this amino alcohol is connecting to the phosphoric acid again through a ester bond. So 1, 2, 3, 4 bonds to connect all the 5 molecules. And then you have your glycerophospholipid. So this is your polar head. This is your non-polar tail. So these glycerophospholipids, again we discussed this in cell membranes, are the components of cell membranes and help in the transport of and communication and transport. Again, draw the condensed structural formula for lecithin. This is the other glycerophospholipid, using myristic acid for the fatty acid and choline as the amino alcohol. Sorry. So myristic acid, here we have to do it ourselves. So you will first start with the molecule of glycerol. Now myristic acid, again, what is the composition? There are 14 carbons and no double bond. So you are taking a molecule of glycerol, taking 2 molecules of myristic acid, 14 carbon, no double bond, connecting 2 hydroxyl groups of the glycerol to 2 acids using an ester bond. How do you do that? You eliminate a molecule of water and connect the hydroxyl and the carboxylic group together. Then you take a molecule of phosphoric acid, connect it to the 3rd hydroxyl, and connect choline, your amino alcohol. Where do you find the structure of choline? Again, you are given the structure of choline in the book. Look for the 3 amino alcohols. When you start off glycerophospholipids, you are given structures of the 3 amino alcohols. So pick choline and connect choline through an ester bond to the phosphoric acid molecule. So this will be a practice for you to create your own lecithin molecule, and you will have structures for reference in your book. There are lecithin molecules set up here for you. There is lecithin molecule with choline on page 528. You have to only check if your acid is myristic acid or not. but the rest of the structure is set up for you on page 528. Just make sure you are using myristic acid. Here the acid on page 528 is 14, 15, 16 carbon no double bond. So that is not myristic, so you can replace that for myristic. So you are set. Sphingomyelin, palmitic acid, the 16 carbon saturated fatty acid is the most common fatty acid found along the ionized amino alcohol choline in sphingomyelin of eggs. Draw the condensed structural formula for this sphingomyelin. So we are setting up a sphingomyelin structure. And how does a sphingomyelin structure look like? Page 530. So you have a sphingosine molecule, connected to one fatty acid, and here your fatty acid is palmitic acid, a 16 carbon structure. And you're also connecting the choline and phosphoric acid molecules. So sphingosine, you have the structure of sphingosine on page 530. This is the structure of sphingosine. This is embedded in the sphingosine structure. So you have one amino, NH2, and one hydroxyl OH. To the amino, you connect your acid, eliminating amino ester, eliminating, this is your bond, amide bond. The hydroxyl, you connect the phosphoric acid, and to the phosphoric acid, you connect the choline. So this is, again, your polar head and the non-polar tail. So this is sphingomyelin. The only difference between glycerophospholipid and this is that this is embedded in sphingosine and there is an amino group. But the concepts are very similar between the two. So sphingomyelin. Stearic acid is found in sphingomyelin in the brain. Draw the condensed structural formula for this sphingomyelin using ethanolamine as the ionized amino alcohol. Oops, sorry. Here again, you are going to start with your basic structure. The sphingosine structure, you will start with the sphingosine structure. You will connect stearic acid to the amino group, and you will connect the amino alcohol ethanolamine to the phosphoric acid. So you will keep your basic structure intact. I am going to ask you to look at the previous example, replace the acid, replace the amino alcohol. And this will be a good practice. If you have any questions, please let me know. So now we are looking at cholesterol. Which part of cholesterol is the steroid nucleus? What features have been added to the steroid nucleus in cholesterol? What classifies cholesterol as a sterol? So the 4 fused rings, A, B, C, D, that is the steroid nucleus. So this again, please refer to your book, page 532. Cholesterol molecule is given to you on page 533. Carbon 3 on ring A has the hydroxyl. There's a double bond in the second ring, ring B. There is a methyl group at carbon 10 and a methyl group at carbon 13. And the carbon 17 has a branched carbon chain. So these are the features that make a steroid nucleus a cholesterol molecule. So the hydroxyl group, the double bond, the 2 methyl groups, and the branched carbon chain. These 4 components, when you add these to the steroid nucleus, you create a cholesterol molecule. The hydroxyl group, OL, sterol, OL, that tells you there is a hydroxyl group. So from alcohols way back in the beginning, we said any name with OL ending in OL is an alcohol, hydroxyl group. Why is cholesterol in the lipid family? Again, the basic definition of a lipid is insoluble in water. And that is the characteristic that makes these lipids. It's come from a Greek word lep, that is insoluble. Describe the phospholipids in the lipid bilayer. The phospholipids, the glycerophospholipids that make up the bilayer have two parts, polar and nonpolar. The cell membrane, an alignment of nonpolar sections towards the center with the polar sections to the outside, produces a barrier that prevents the contents of the cell from mixing with the fluids, separating the contents within to the contents outside. That is the role. First role is separation of the contents within and outside and inside the cell. The second is also acting as a permeable membrane to let the contents move back and forth, mixing with the fluids on the outside cell. They prevent the contents from mixing, but also effectively communicating with the outside environment. That's also a part of the components embedded in the membrane, but also letting the particles pass through inside and out depending on the need. So role, that is the role of the lipid bilayer in the cell membrane. What is the function of cholesterol in the cell membrane? What did we say cholesterol was doing in the cell membrane when we were discussing cell membrane? We said that there are three particles that are embedded in the cell membrane. There are proteins, there are carbohydrates, and there is cholesterol present in the cell membrane. So cholesterol, presence of cholesterol adds strength to the cell membrane, and you can find that on page 538 and 539. What is the function of cholesterol? It adds strength to the cell membrane. Protein will provide pathways for particles to move back and forth. Carbohydrates are neurotransmitters and communicate to the hormones and take communications back and forth. So that's what the function of carbohydrates on the cell membrane is.